Welcome back. Uh, in previous lectures, we have developed the theory uh, for Fourier transform for a function defined on R, and we have assumed it to be source space. And then we got the inversion formula, and also we have seen that the derivatives Fourier transform is going to be heated by polynomial times the Fourier transform of the function. So, by using this we can form some sort of strategy how to solve some linear PDE by using these techniques at our disposal. So, just let us see with first with some ordinary differential equation. So, let us see consider the ODE to be y double prime minus of y is equal to f. Let us assume that f is a function in the nice class. Then by taking the Fourier transform from both the side, we have minus of y hat is equal to f hat, and this what we know is that this is 2 pi I xi square y hat of xi minus y hat of xi is equal to f hat of xi. F is a given function. So, this implies that minus 1 plus 4 pi square xi square of y hat of xi, this is equal to f hat of xi. Hence, y hat of xi, this is equal to f hat of xi minus 1 by 1 plus 4 pi square xi square. We know that this has a moderate decay. So, if there is a nice function g such that g hat of xi, this is equal to minus of 1 by 1 plus 4 pi square xi square, because we can take the Fourier transform. This is an integrable function. We know that that is going to be our g hat. So, this is going to be y hat of xi, which is equal to f hat of xi into g hat of xi, which is equal to f convolution of g hat at xi. Now, from the Fourier transform there is a uniqueness we have proved. So, this implies that y of x is equal to f convolution of g of x. Now, in here f is known to us, g is known to us, and then we can find y as the convolution of two known function, which is going to solve the second order ODE. So, now with this little observation, so let us try to consider the linear heat equation. So, now let U is a map from R cross 0 infinity to C, and consider the differential equation that is called the diffusion equation or heat equation. Consider the initial value problem. What is that? This is u t, that this is a u is x comma t, where x is the space variable and t is time variable. So, u t is where del u by del t of u, and u x is del by del x of u. So, u t is equal to some c times u x x, this is on r cross 0 infinity, and then u of x 0, that means on the boundary. So, u is a map which is defined on this upper half plane and this axis is not there. Now, when the boundary of this domain is going to be the real axis x axis. So, on this we are giving the value f of x on R. When t equal to 0, that is going to be the boundary. So, now consider this equation. So, now we will have a strategy how to solve this equation, and for notational convenience let us assume c is equal to 1. And of course, we will assume some nice property. For the time being, we can think of that f is in the Schwarz space. So, and f is in the Schwarz space. Okay. So, now we have the equation to solve u x x, this is equal to 0. Take the Fourier transform on the space variable. That means, u hat at xi t, this is integral minus infinity to infinity u of x comma t e to the power minus 2 pi I xi x dx. That means, for each t we are taking the Fourier transform on the space variable. So, by taking the Fourier transform, we get u t hat of xi t minus u x x hat at xi t, this is equal to 0. Now, let us compute what is u t hat at xi t. This is integral minus infinity to infinity u t of x t by definition e to the power minus 2 pi I xi x dx. Now, if this is del by del t, so I can take this out, del by del t of minus infinity to infinity u of x t e to the power minus 2 pi I xi x dx. This is equal to del by del t of u hat of xi t. You see, u t hat is u hat of xi t. In a sense, what we are saying that with this observation, the operator which is one operator is the time differentiation operator, another is the space Fourier transform, they are commuting. So, here first you take the derivative, then you take the Fourier transform, here you take the Fourier transform, then you take the derivative with respect to t. So, now for the second term, so what we know is that u x x hat at xi t, then that means we are taking the double derivative with respect to x and then taking the Fourier transform. So, this is 2 pi I xi square and then u hat of xi. So, this becomes minus 4 pi square xi square u hat oh, you had of xi comma t for each t xi t. So, what we have got is that if we define, then what we have got for each xi, define phi xi of t, this is equal to u hat xi comma t. So, then this equation is saying that u t hat is del by del t of, so this is d by dt of phi xi t plus minus of this, that means plus 4 pi square xi square phi xi t is equal to 0. So, in other words, this is a ODE which is written as plus 4 pi square xi square phi xi is equal to 0. Now, this is an ODE. So, we know exactly what the solution it is going to be, and this equation also, now the solution is going to exist, because if you look at phi xi at 0, then this is u hat of xi of 0. And what is u of x 0? We know that this is f of x. Therefore, u hat xi 0 is equal to f hat of xi. So, this is equal to f hat of xi. Now, combining these two, this is has a solution, and this is existence of the solution will tell us that phi xi of t, this is equal to phi xi at 0 e to the power minus 4 pi square xi square into t. This implies that u hat xi comma t, this is equal to f hat of xi e to the power minus 4 pi square xi square t. And this is a pretty well known thing. Now, define for each t greater than 0, define h t of x. This is equal to 1 over square root of 4 pi t e to the power minus x square by 4 t. So, this is called the heat kernel. Now, one can compute this h t hat at xi, this is equal to e to the power minus 4 pi square xi square t. That is not too hard to see. So, because if you can think of, this is easy, we can see it in a minute, that take k of x is equal to e to the power minus pi x square. And then we know that if we define k delta of x, this is equal to 1 over delta k of x by delta, and take delta to be equal to 4 pi t, square root of 4 pi t if I am taking the delta, then this is equal to 1 over delta e to the power minus pi x square by delta square. So, this is equal to 1 over square root of 4 pi t and then e to the power minus pi x square by 4 pi of t. This is equal to 1 by square root of 4 pi t and e to the power minus x square by 4 t, which is nothing but our h t of x. So, therefore, h t hat at xi, this is equal to k delta hat at xi, and we know that this is k hat of delta xi. So, k hat of xi is e to the power minus pi xi square. So, e to the power minus pi delta square xi square, and which is equal to e to the power minus pi into this is 4 pi t into xi square, which is equal to e to the power minus 4 pi square t xi square. This is precisely what we had claimed. Okay, so coming back to this, so what we have seen here is so u hat of xi t is equal to f hat of xi e to the power minus 4 pi square xi square t. So, therefore, u hat of xi t, which is equal to f hat of xi, and then this h t hat at xi, which is equal to f convolution of h t hat at xi. So, u of x t, this is equal to f convolution of h t of x, this going to satisfy the is a solution of this equation. Okay. So, now what we have got, let us write it down in terms of a theorem. Given let f belongs to the Schwarz space and u of x t, this is equal to f convolution of h t of x t greater than 0. Then 1, u is twice differentiable in x and t on R2 plus in the upper half plane and solves heat equation. This is what we had observed. So, now secondly, u of x comma t, this converges to f of x uniformly in x as t goes to 0. This is what we will prove, and third one is that so in particular here, so now u x t, which is defined the upper half plane, and when t goes to 0, we are coming to the, just look at the picture, u x t is defined over here. When we are coming to t 0, so we are coming to this line. So, now we can write the closure of the set of our upper half plane, this is equal to x comma t such that x belongs to R and t greater or equal to 0. So, what this statement is saying that as a matter of fact u is also continuous on this domain. That is, in particular, this is what the second part is saying, and also minus infinity to infinity mod of u of x comma t minus of f of x square dx, this goes to 0 as t goes to 0. Okay. So, you see, the first we have already seen in the previous one. Now, we will prove the second, which means, so proof we have verified 1. Now, for 2, now what it is saying? So, now as we have observed h t is of x, this is equal to k delta of x, where delta is equal to square root of 4 pi t. So, therefore, u of x t is equal to f convolution of h t of x. We can write that f convolution of k delta of x. Now, if t goes to 0, if and only if delta goes to 0, because delta is square root of 4 pi t. So, now we know that k delta of x is a good kernel. Now, f is in Schwarz space, therefore, what we have seen that this converges to f uniformly as delta goes to 0. That means, what we get is that u x t, hence u x t converges to f of x uniformly as delta as t goes to 0. Okay. Now, for the third part, we want to see that minus infinity to infinity mod of u of x t minus of f of x square dx. You apply Planck's rule. So, this will Planck's rule will tell us that this is u hat of xi comma t minus of f hat of xi d xi. Now, we know precisely what u hat of xi, this is f hat of xi into h t hat of xi, that is minus 4 pi square xi square t, and then minus of f hat of xi square d xi. This is equal to integral minus infinity to infinity. We can pull out the f hat of xi square. So, we are left with e to the power minus 4 pi square xi square t minus 1 mod square d xi. Now, we know that if f is in Schwarz space, then f hat is going to be in Schwarz space. Therefore, for a given epsilon, there exists a n such that integral mod xi greater than n mod of f hat of xi square d xi is less than epsilon by 2. So, now what we do is that we break this as mod xi lesser equal to n and this integral mod xi greater than n. Now, you can see that this part is less or equal to 2 times mod xi greater than n mod of f hat of xi square d xi, which is less than epsilon. Okay. Now, for the first part, what we can do is that you 4 pi, this is e to the power. So, now on this, so whenever we have a t going to small, so this one is going to 0 as t goes to, and this is a compact interval, therefore, it is uniformly it converges to 1. Therefore, this one e to the power minus 4 pi square xi square t minus of 1, this is less than, let us say, epsilon by 2 n. So, you can pull this out, the first one will also become small, 2 n into 2 n plus epsilon, which is 2 epsilon. So, this becomes a very small quantity, this entire thing will go to less than epsilon by 2 n. So, hence what we have got, that this converges to 0, this as t goes to 0. So, natural question one would like to ask at this stage, yes. So, here we have seen that f convolution of H t is a solution for the heat equation we have considered. In one method we have got this. Now, is it necessarily true that this solution is unique? And in the next lecture we are going to address that issue. Thank you.